Hello everyone, and let's start today's video lecture. And in this video lecture we will be learning about graphical representation of motion. So we have understood what a motion is, how to write the equation of motion, and also we have understood what is the graph and how to plot the graph in calculus. In calculus we learned this. Now we are going to combine both together. So we have understood if we need to plot a graph, we need to have a coordinate axis. So let's say these are two axes. We have to name them depending upon the parameters we are using. And if we are using x and y, so we call them as a y and x. If we are using another parameter, we will be using their name, right? And if we know the equation, then we can plot it. And we have understood so many plots like straight line graph, parabolic graph, or circular, ellipse, and all that. We know their equations, and we also know how they look like. So in this particular part, we will be learning how equations of motion can be plotted or represented in the graph. So we will start from the very basic one, and there are certain basic graphs that are very important, and they are let's say start with this first, called position versus time. So whenever any motion is taking place, then we need to know how the position is changing with respect to time. So we call it as a position versus time graph. So this will tell us position variation over the time. So what we are going to do, we are going to write this as a this as a position. Now if it is one dimension, you can measure the position by x. If it is multi-dimensional, you can measure the position by r later. And this is time, and time for t. So sometimes we also call it as x versus t graph. And we also mention the unit, like this is in meter, this is in second, so that will be given to you. There can be several type of graphs, right? So let me start the basic one. The most basic graph could be like this. If it is like this, so what we are going to conclude from this? Can we conclude anything out of it? Yes, of course. It says when the time was 0, the position was this. This number could be, let's say, x naught. When time become 1 second, still position was x naught. Time become 2 seconds, still position is x naught. 3 seconds, still position is x naught. That means as the time passes, the position does not change. Position remains the same. So this is basically indicating x is equal to x naught. And this x is equal to x naught is for all values of t. That is permissible. So for all given values of t, this x is equal to x naught. And whenever this is the case, that means we say particle is or object is not changing its position. And whenever there is no change in position, that means the object is at rest, because it's not changing its position with respect to time. So our conclusion will be that the graph is representing an object which is at rest. So this is state of rest. State of rest. Understood? Basic graph, that means position over the time, how it is changing. If it is not changing, then it is at a state of rest. And next graph could be like this. So let me put this next one, and this is passing through origin, and it is like this. And this is representing again position versus time graph. We need to keep one thing more in mind, that this, whenever there is a time graph, right, so this domain will not be considered, because this is indicating t negative, and whenever we start observing any motion, we generally start it from t equal to 0, and then when it goes onwards. Alright. Yes, the graph can be in this negative domain if we start, let's say, t from 10 seconds. So if we are starting from t from 10 seconds, then somewhere backside will be t equal to 0, right? Then this will not be origin in that case. You like this, if this will be t equal to 10, and if someone consider deliberately this origin as a t equal to 10, That a different story, but that will be rarely the case. And in general, you'll find this is origin, and origin is always is indicating 0, 0. So this territory is t negative, and that will not be feasible because time cannot go backside. Time does not flow in negative direction; it flows only on the positive direction. So time is unidirectional. So that time is a scalar quantity because it is only in one dimension, only in one direction, not in the backward direction, right? Anyway, so nutshell point is wherever the t negative, that graph is not existing. That you need to keep in mind. And this is a motion. Then what it says, when the particle was origin, time started. That means time was 0. As the time passes, position increases. Time increases, position increases. Time increases, position increases. That means particle is moving. So it's a state of motion. And if it is a state of motion, so we can find the other information like at what time, where the particle is located. Moreover, another important point that we need to keep in mind in this x versus t graph, if we find slope is going to be equal to d this axis upon d this axis, right? So it's going to be dx upon dt. Then we come to the equation of motion, and we can immediately realize that this is indicating velocity. So slope of x versus t graph gives us velocity. That is an important information. So whenever there is an x versus t graph, you just measure the slope and you can claim what the velocity is. Here this is a straight line having constant slope. A straight line always has a constant slope, so that's a theta. Let's say if it is theta, so we can say slope is going to be tan theta. So velocity is going to be tan theta. So we will say this motion is uniform motion. Uniform motion. So what is a uniform motion? Uniform motion is a motion in which velocity remains constant. That means velocity is constant. So if sometimes question asks for uniform motion, then you mean uniform motion means velocity is constant. And further information you can say, if velocity you got to know, so what the acceleration is going to be. Acceleration is the rate of change of velocity, and velocity is a constant, so acceleration is 0. So see, what we are doing basically, we know a graph, position versus time, and we are able to find all the quantities like position, velocity and acceleration over the time. This is what the kinematics is. So kinematics can be explained or described using the graph. So one graph can let us know all the informations. Like here, at any time you can read from the graph what the position is, and then measuring the slope you can measure what the velocity is, and once you got to know the velocity you can claim what the acceleration is. So here acceleration is 0, velocity is constant, position is increasing over the time. That's what we can claim. Let's consider next example of position versus time graph, which is shown in this figure. And there are lists of points A, B, C, D, F, G, H. These points I've shown. So from this graph we can again read all these things like at what time, where the particle is. If you are given time, so you just go ahead and look for this number. So that number is going to give us the position. So you will get the position at all times. So if the graph is x versus t, that means you know x for all the time. That's how this graph has been plotted. Now then our purpose would be to, since we know this x over the time, we need to know what this v is going to be, how to get the velocity at different points. Then our purpose will be how to get acceleration at different points to describe this entire motion, right? So let's say we are interested about certain points, and let me describe this. Let's say we are talking about the A point. So what is happening at point A? Can we say something? At this point A, we will find this is the position of the particle when time started. That means this is the initial separation. This is the initial separation of the particle from origin. That means particle starts from the position A, and that is initial separation. So we can say particle is at OA distance from the origin initially, and it is in the positive x direction and direction. So it says in short, if I write particle starts from OA distance or displacement or position OA distance from origin. From here it starts, and whether it has a velocity, so you say yes. After this point you will find if you draw a tangent, then a tangent is going to be having a positive slope, so it will start moving in the positive x direction. So it starts moving in the positive x direction, right? So and moves positive x direction, moves in positive x direction. This is what we can interpret for point A. So since it starts moving, that means there is an acceleration as well, because starting, so it will be moving with some acceleration. And what about point B? Can we claim about point B? A to B, if you try to draw a slope, if you draw the slope, then there will be a slope, but the slope is going to be decreasing. So start with velocity, and then the velocity decreases, right? So it does not start from rest, it starts with certain velocity, and that velocity is decreasing. So that means it's not having an acceleration, rather it is having a deceleration. We can claim that part. And at B point you will find dx by dt is 0. Dx by dt, that is slope, is 0. That means momentarily particle is at rest, so velocity is 0. After B point you will find the slope becomes negative, that means velocity becomes a negative x direction. So at B point it is coming at rest, and then velocity becomes a negative direction. So at C point you will find velocity is negative because dx by dt is negative. Hence velocity is negative. That means negative velocity means moving in negative x direction. So from B to C, it is B to C, it's moving in negative x direction. Further, C to D is also it's moving negative x direction, and D to E is still moving in a negative direction. That means from B to E, this motion is in negative x direction because slope is negative. What is special for the D point? At D point you will find this coordinate becomes 0. That means position becomes 0. If this position becomes 0, that means particle is at rest. Particle is at origin and moving in negative x direction. So meaning is particle is at origin, x equal to 0 means it comes back to origin again, and it is moving in negative direction, and it is having velocity negative. Once you reach to this E point, then you can claim that at E point velocity becomes 0 momentarily, and it's changing direction. So from negative direction, now it's moving in the positive direction. Beyond this, it will be moving in the positive direction. Again at point F, you will find this position becomes 0. That means it is again crossing the origin, but this time moving in the positive x direction. And at G point you will be able to find dx by dt is positive, so velocity is positive, it's moving forward, right? And at B point and this E point, it is momentarily at rest. So if it is momentarily at rest, then we cannot claim that this acceleration is 0. So what the acceleration is going to have, so at B point velocity is 0, we can claim about acceleration, because acceleration is d2x upon dt2. And if you look carefully, this is local maxima, and for local maxima you know this d2x upon dt2 has to be negative. That means acceleration has to be negative. So acceleration is negative, that means it is retardation. So it was retarding, and then at B point it is retarding. That's what we can say. Or we can say from here the velocity was positive, then converting into negative. That means velocity is converting from positive to negative. That means first is becoming 0, then increasing in the negative direction. Hence it is a retardation. Similarly at E point we can claim, at E point you say this is a local minima. So acceleration is d2x upon dt2. From here you can connect. I'm trying to make you connect with mathematics. So this local minima for this is positive. That means it is acceleration. So E point, it is acceleration because velocity is increasing from negative direction 2, earlier it was negative, then becoming positive. So here the velocity is increasing. So this is how we can describe the entire motion of this particular graph, which is x versus t. So if you point to remember, slope is the velocity and the rate of change of slope is the acceleration in case of position versus time graph. Now let's try to visualize this motion practically, how it's going to take place. So that's a straight line and this is x direction. So this is a picture, not a graph. This is a graph. So let's see how it look like in picture in real sense. So let's say this was your object. So this object was initially at positive x direction, so it was somewhere here at t equal to 0, and it was moving in the positive direction, so it has a velocity in this direction. So this is indicating point A of this particle. Then this particle goes forward and comes at rest momentarily this point. So this point is B. Then after what it does, it returns back by following the same path. And after returning back, it is going to cross somewhere this origin again. When it is crossing this origin again, so that point is D point. So this will be again coming at origin and moving in the negative direction. So that is the D location. And in this D location, it keeps on moving, and somewhere its velocity decreases. That means it comes to rest momentarily again. So that point is E point, where it comes at rest. Once it has came at rest, then after it won't move in this direction, it will change its velocity to positive direction. So again it changes its velocity like this. So let me write D at somewhere else, and this will be moving in this way, and then future it keeps on moving in this direction. This is how the particle is moving. So this was the location back to D, this was E, and then again when it was crossing this origin, this situation. So this situation when the crossing origin was the location F, and then further there was a G location somewhere, and then it's moving in this way. So it's going to move in future like this. You can think of how the particle is moving in actually. So this motion is being described by this graph. Let me say again, it starts from positive location. So I started with a positive location. This was t equal to 0, and then it was having velocity in the positive direction. So it has a positive direction velocity, comes to momentarily at rest with B, because at B it wanted to change its direction of motion. So it's momentarily rest at B. And you see at B its velocity have been changed from positive direction towards negative direction. That means acceleration must be in this direction. That means A must be negative. That means retardation. And then you can connect that this is moving with this retardation and going to this direction. And then after at D point you will find again it's crossing the origin. Then again acceleration changes its position. Direction, then it becomes retardation for this motion. So acceleration becomes in this direction. That's why you see at this point A becomes positive, or A is positive. Then after changing this position, this direction, then it moves in the positive direction, and forever then onwards it will keep on moving in the positive direction. Okay, so that's how motion can be imagined by looking at the graph. Another important graph is velocity versus time graph, or V versus T graph. In this you'll find V will be plotted in this vertical direction and T will be plotted in this. So when we say V versus T, so the first letter is plotted in the vertical axis and second letter is plotted in the horizontal letter. That's how the nomenclature goes. It can be of any type of graph. So let's consider any random graph. Let's say this is a graph. So some points are very important that need to be followed, like 2 points basically that we are interested in. First is slope. So if you measure the slope of V versus T graph, so this slope is going to be equal to dV by dt. And we know this dV by dt is acceleration. So whenever you measure slope of V versus T graph, you will get the result as acceleration. And then another is area under the graph. So if you measure this area under the graph, or area under V versus T graph, this will give us the displacement of the particle. So that's going to be integration V dt. And we know this integration V dt is a dx, which will become x. So that becomes displacement. Displacement during that time duration. So let's say we are interested in this from T1 to T2. So this area under the graph means area under the graph, and these time boundaries and this horizontal axis. This area is indicated as integration v dt and limits running from T1 to T2. And this will be indicating the displacement from T1 to T2. So that's going to be displacement of particle or object, whatever is moving, between the time duration or from t equal to T1 to t equal to T2. That's what the meaning is. So point is, if velocity versus time graph is known to you, you can easily measure velocity with respect to time, because they are going to be the direct points from the graph, and you can measure acceleration by measuring the slope, and you can measure displacement by measuring the area. So you can get all the information regarding to that motion. So this will be velocity versus time graph, and it's a very popular and important graph. Now if we consider the easiest graph or most basic graph, so that would be a straight line parallel to time. That means this quantity does not changes over the time. So you will say what this motion is going to be. So can you think of what this motion is going to be? This is going to be particular velocity. Let's call it as a u. So at t equal to 0, the velocity is u. As the time passes, the velocity remains u. Then again it remains u. That means velocity remains constant. So this is a graph of constant velocity. So you can say it's a uniform motion. Uniform motion. And we know whenever this is uniform motion, then acceleration is 0, or we can also say this is a horizontal straight line, so acceleration is going to be slope is going to be 0, so acceleration is 0. So that means this is with constant velocity or uniform motion, right? And is it at rest? No, it's not at rest. It's moving with a constant velocity, and acceleration is 0, so you can find the position at any time just by measuring u and t. So this equation you can apply, and you can find the position, or moreover you can find the area if you are interested. Let's say you need to find the displacement for this time t1 or t0. Just measure this area. This area is going to give us x, the displacement, which is going to be u t0, which I wrote just here in terms of equation, right? So that's a simple way of finding position, displacement, and acceleration. If we go a little bit further, so we can consider this graph again is a straight line, and if it is straight line, so this velocity is known as initial velocity. You can call it as u, and its velocity is increasing. So you'll find its slope is a constant. So slope is constant. You can see slope is acceleration, and this is coming as a constant. So you will find this acceleration is constant. And we have already understood what happens for a constant acceleration, one-dimensional motion. There are particular equations, right? 3-4 equations. So we can prove all these equations by using this graph as well. So let's do that thing quickly. Let's t equal to 0. This velocity is this. And let's consider any time t at which we are interested to find this velocity. So if we consider this time t, then you need to go move vertically up, and then you need to go this time horizontally, and this velocity you will call it as a v. Okay, and then we can have some supporting constructions, like we can have this way, and this is going to be definitely vertical. This is going to be 90 degree, and this angle is that's a theta, because we need to measure the slope. So can we say what is the tan theta from the triangle is going to be? What I'm trying to do here, we are proving those equation of motion for the case of constant acceleration, because this graph is indicating that particular motion. So we can say, let me write a proof or something. Proof of equation of motions. So can we say that here tan theta is visible? What is that tan theta? Tan theta is the slope, and this slope can be found from this triangle. That's going to be this side. What is this length? This is v, this is u. So can we say this is going to be v minus u? And what is this length? It's equal to the t for time. So tan theta is perpendicular, which is v minus u divided by t. T is the base dimension. Moreover, slope is also tan theta. So we know slope is also tan theta, which is equal to a. So this is equal to a. As you equate this and simplify it, you will get to know v is minus u is equal to 80. So from here you will get to know v is equal to u plus 80. So that's the first equation of motion, and that can be proved using this graphical analysis or graphical way, and this is for a constant acceleration case. Similarly, we can go for the proof of the second equation, and for the second equation we can measure this area under the curve, because displacement is given by the area under the curve. So let's say we are measuring this entire area. This entire area we need to measure, because graph area with the axis, that's what we measure. This area can be measured in two forms, this triangular area as well as this rectangular area. So for second equation we will be writing this: displacement, that is x, is going to be equal to area under the graph, area under the graph. So can we find that area under the graph? So you say area of triangle plus area of rectangle, or area of rectangle plus area of triangle, because addition works both ways. So what is that rectangular area? Can we see that rectangular area which is downside? It will having two dimensions. One dimension is this, that's a u. Another dimension is this, that's a t. So you'll find it's u into t plus area of this triangle. Can you see the area of this triangle? Yes, we can see that area is going to be half base, which is t, into height, which is v minus u. So that becomes the position x as a function of t and v. Now we can put the value of v if we are interested. So v minus u is equal to 80. We can substitute here. So x will come out to be ut plus half t into 80. Half t into 80 will make it 80 square. So it will become x is equal to ut plus half 80 square. So that is how your second equation of motion is proved. And we have already talked about, if you know these two equations, first equation and second equation, then the third equation can be manipulated by can be found out by manipulating this t from there to there, and we can also work for the fourth equation. So these two equations are basic equations that we can find out using the graphical analysis. So this proof is important for you, particularly for your board examinations, where they ask to prove these equations based on the graphical representation of motion. So you need to start with this graph, write everything that is written over here, and hence you can prove that, right? Let's consider another example in this v versus t graph itself, and try to interpret this, what these points are going to have the values. So we will say that t equal to 0, particle starts from A. So whatever this is going to indicate u, that means initial velocity. So initial velocity will be measured by this this vertical coordinate, and the slope will let us know. Slope is a positive, so acceleration is going to be positive. So at point A, acceleration is going to be positive. Making sense or not? And then this acceleration, positive acceleration, is decreasing over the time and it's becoming 0. So at point B, you will find acceleration will become 0. So at B point, acceleration will become 0. And then this acceleration, that is slope. So we are measuring the slope. Slope becomes negative after B. So at C point, you will find acceleration is going to be negative. So we can say, like for point A, initial velocity you can read. And you can also talk about the acceleration, which is positive. For point B, you will find this acceleration is 0, and velocity is non-zero. And you can say velocity is maximum. Velocity is maximum, right? And then it might be asked that what about at C point? So you can measure the velocity at C point is going to be somewhere between 0 and B. Point's velocity, and this slope is going to be negative, so acceleration is negative. That means deaccelerating velocity is decreasing. When you reach this point D, what happens? Acceleration is still negative. That means it is negative acceleration slope, because slope is negative, but the velocity becomes 0. So velocity is 0. That means particle is momentarily at rate at point D. Then come to point E. When you are at the point E, you will find the velocity is least, it's a minimum, and it's a negative, of course. So V is minimum. Moreover, its acceleration is 0, momentarily 0, and its acceleration is changing. Earlier it was negative, now it's becoming 0, later it will become positive. So this at point F, when you reach to this point F, you'll find velocity becomes 0, but acceleration is positive. A is a positive. Similarly, at G, you can claim something like that. Velocity is increasing, so A is a positive. A is a positive. Velocity has some value, and it is increasing. As far as the displacement is concerned, so you say initially it was somewhere, and then its velocity is increasing. So this is the displacement. This area is forming the displacement. So particle is going ahead, and at D point, particle is farthest from the initial position. And then when it comes to further time, then you'll find this displacement becomes negative because velocity is negative. This additional displacement is negative. So this is a positive, this is a negative. Though negative part is smaller, then still it is in the same direction, but it has reduced, because we know this will be treated as a positive area, this will be treated as a negative area. So if question asks what is the farthest separation up to this point F, then you say at this point it goes to the farthest, then returns back to somewhere, and then after this point F, again it starts moving this. So if we need to draw this in a picture like this, let's say this is origin from where it start, particle. If you start the particle from here, then you'll find this particle moves with certain velocity, keeps on moving, and when it comes to the D point, then it changes its direction. So up to D point it moves in that direction, and then it returns back. When it returns back, so this displacement now is reducing because of this, it's coming back. So here the displacement will be only this part, it's reducing, isn't it? And how much that reduced part will be, that we can find out. And it happens up to the point F. When it reaches to the point position F, you will find again this velocity becomes 0, momentarily raised. Whenever the velocity is 0, it changes its direction, then it becomes positive. Then again it returns in this way, and then it keeps on moving forever. So it changes its direction twice, one at D point and one at F point. Whenever it changes its direction of motion, then you'll find the velocity has to be momentarily 0. So velocity is 0 at D, and velocity is 0 at F, and it's non-zero at anywhere else. So where the particle is at farthest, well, if it is going there, so farthest distance can be furthermore, but if you are looking up to F point, then you'll find this OD is the farthest distance and not the OF. OF is this least separation starting from D and up to F, right? And similarly, we can say later on this displacement keeps on increasing, and if you consider more time, it can be the maximum among all. So this is velocity versus time graph, very, very important. And how to what are the points that you need to keep in mind? One, slope is going to give us acceleration, area is going to give us displacement. Next important basic graph is acceleration versus time graph. So whenever there is acceleration versus time graph, important point that you need to keep in mind is the slope. So if you measure the slope, you are going to get it as a dA by dt. And another important is area under the graph. Area under the graph. So in all graphs, we will be looking for these two things, area under the graph and the slope. And then we will say which quantity is useful for us and not. So this is going to be A dt. Now dA by dt is not any physical quantity that we have defined, right? So we will say if somebody asks what the slope gives you in A versus t, so you say it's the rate of change of acceleration with respect to time. That's what it gives. Is this any physical quantity? No, this is not any physical quantity, but it is rate of change of acceleration. So this will not be so important for us. Let's check about this area under the graph. This is A dt integration, and you know this will become dv. And if you are going from t1 to t2, from one time to another time, so you might be moving from v1 to v2, one velocity to another velocity. So this will become final velocity minus initial velocity. These are velocities. That means it is change in velocity. So area under the graph is going to give us change in velocity. So we can read this change in velocity from the area under the graph, and we can find out our answer. Okay, so this is most important point that we need to keep in mind. And how the graphs could be, the basic graph could be like this. If the graph is like this, so we will say this is a constant acceleration case. So we will say A is a constant. It is not a uniform motion, it is a constant acceleration motion, so we can apply equation like V is equal to U plus AT and all that stuff, right? So this will be the basic graph if we are using a straight line which is parallel to the time axis. Another could be like this is type of a straight line, so you will say this is not a constant acceleration graph. So if this kind of graph is given to us, so we will say A is a variable. And here we cannot apply this equation V is equal to U plus AT because its validity is only for A is to constant, so this is not true, not valid rather. So how we are going to proceed with, we will be solving it by using the concept like this and otherwise. So let me give one example. So let's consider this example that is written over here. It says a particle starts with 10 meters per second, that's initial velocity, and moves on a straight line, and acceleration is as shown over the figure. So that's the acceleration is given to us. We need to find the velocity at equal to 4 seconds. So can we find the velocity at equal to 4 seconds? So what we need to do, this is a graph, right? So how to get the velocity? So we say the change in velocity, the formula goes like this. Point is this, change in velocity is going to be area under the graph, area under the graph, and change in velocity means final velocity minus initial velocity is equal to change area. So we need to find 4 seconds, so we need to go for 0 to 4. So this area we are interested. Can you find this area? Yes, we can easily find this is a triangle. So half base, how much the base is? Base is 4 into height. What is this height? This is 6. So that's a 6. So this will come 12 basically. So we will get it like V minus 10 is equal to 12. So what the V came out to be? 22 meters per second. That's our answer, right? So if this is a variable acceleration, we can easily handle by using this formula. Change in velocity is equal to area under the graph. So here is a question, very similar question that we just finished, and you need to solve this and you need to answer. Still you need to answer the same thing, that means velocity at equal to 4 seconds. But the graph is different, so we need to find the velocity at this 4 seconds. So look at this graph, solve and find this answer and comment in the comment section below. So here is one more example related to this graph, and it reads like this. A ball is dropped from a height on the ground. The ball reaches back to the same height after bouncing back from the ground. Then for this entire motion, draw the following graphs. Position versus time graph, one that we need to draw. Velocity versus time is another that we need to draw. Acceleration versus time is another that we need to draw. And we need to consider the direction upward as a positive. And the question will also indicate where to choose the origin. So let us first draw the picture, how it's going to look like. Rough picture. So let's say a ball is being dropped from here. This is the ball that is being dropped. And let's say this is capital H height. So if you drop it, it is going to come back or come downside in this manner. And then hit it. It will hit the ground. When it is hitting the ground, it will carry maximum velocity because this velocity increases due to gravity downside. So gravity is acting downside. So it will be acting as acceleration when it comes downside. After hitting back, it will be going back to the same position. And if it is reaching to the same position, that means it is hitting in such a manner that whatever this velocity was, is V0, let's say, so it regains the same velocity. Because if it regains the same velocity, only then it can reach up to the same height. Okay, so this is kind of motion we are visualizing. And we need to consider upward direction as a positive. So again, there will be mentioning of origin. So we are considering this as an origin. So here we are considering the origin on the ground and upward direction as a positive direction. That is what the parameters we are choosing, or this is how we are choosing the directions. Origin is on the ground where it strikes, and its upward direction is a positive. And if somebody says that consider this as an origin, So you consider this as origin and upward positive, so this displacement will be negative. Okay, so accordingly graph will change. So let's consider for this case, and we need to plot all the three graphs. So first is I have written as h means location. So if the particle is located at this location, so we need to find this displacement. This is going to be displacement or position, or we can call it as a height. So sometimes it is called as a height. So height versus time. So height will give us a position, velocity versus time, and acceleration versus time. The easiest one is acceleration versus time. So in this entire journey, acceleration is given by g. And since upward direction is positive, so we will write a as minus g. So in this entire journey, acceleration will be minus g, and so it starts from here t equal to 0. As time passes, acceleration remains the same. As it goes up, acceleration remains the same, g downside. Only the moment when it hits the ground, at that moment you'll find there will be some force exerted by the ground, and hence the total force on this ball or the object will not remain mg. Rather, some force will also come in the upward direction. So at that moment you will find acceleration will not be g, rather some value. So that is very difficult to identify. So that's a random value or big value is going to come in. So we can plot the graph like this. If we need to plot the graph, so we will say acceleration versus time is going to be negative g, that is minus 9.8. So here somewhere minus 9.8 will be visible, or we can say minus 10 if we are following this meter per second square. And the graph will be going like this, and suddenly it will be broken and then going like this. Can you think of why this is being broken? So you say this is the time when the particle hits the ground. So that's the time when it hits the ground. Let's say that time is t equal to t naught. So we will say up to t naught time it's constant minus g, then again constant minus z, but at that instant it is not defined. So we call it as a not defined. Fine. Now let's come to the velocity. So at any instant, how we can write the velocity of the particle? So we will write the velocity at any instant is going to be equal to u plus at, because constant acceleration motion. So u is for this journey, let's consider for this journey, u is going to be 0, and the g is downside, and so it's going to be written minus g into t. So velocity is going to be minus gt. Minus gt is a straight line with a negative slope. So for this journey you will find v is equal to minus gt is the equation. And how to plot this minus gt? This is a straight line passing through origin, having negative slope, so it will be looking like this. So we can draw like this. It's a straight line like this. So velocity is basically increasing in negative direction and becoming maximum when it hitting the ground. So this is going to be maximum in negative direction, or v naught, you can say minus v naught. Minus means negative direction, and then and this time is going to be that time when it hits the ground. What happens just after hitting? Can you see that? Velocity remains v naught, but it's no more negative. It becomes positive because this velocity becomes in the upward direction. So at the same moment of time, you'll find the velocity will become positive v naught. And then as goes up, it will start decreasing and becoming 0 later on. So you'll find again it's going to follow a straight line and some sort of this parallel slope. Right. So this will be the situation for this will be the graph for velocity versus time, and this is the during falling down, this is rising up, and starting with this same velocity magnitude as it was hitting the ground, but in opposite direction, right? So this direction was this, so that's why it's written positive. So we have written this velocity and acceleration plot. What about h? So for h we need to again write the equation for h. Third equation, let's consider this journey. So displacement during downward direction, displacement is going to be y is equal to 0, and this y is going to be basically downward direction, right? So that you will write as a minus y. So minus y is equal to minus half gt square. So basically y is going to be gt square, half gt square. But we are measuring h. So we can say this h is going to be capital H minus y, isn't it? So it's getting h minus half gt square. So if you look this equation is h is equal to some constant minus half gt square. T square term is coming, so it's parabolic. Minus term is coming, so it's parabolic downward opening. And t equal to 0, it will start from h. So when t is 0, then you will say start from the maximum height, that's h. And then when t becomes t naught, so h will become 0 because it will hit the ground. So this will be coming downwards, opening parabola and hitting the ground at that time. That time is t naught. And then after it will be rising up. Further, this will be again forming the similar parabola but rising up. So it's going to be rising up to the same height. Right. So this will be the time t naught. So at t naught it hits the ground in position, so height becomes 0, and this in further rises to the same height. At t naught acceleration is indefined. At t naught velocity is suddenly changing or abruptly changing. So these are the graph between various parameters like position, velocity and acceleration with respect to time for this particular motion. So draw them and understand. If you have any question or query, you can always ask. So this video was concerned with the graphs and the interpretations of the motion. So that's all for this video. Thank you everyone.